declare ionic bonding as covered as we need it to be and go on to covalent bonding, unless there's some question. Okay. Now, in ionic bonding, we attribute the stability of the compound to Coulomb's law effects, lattice energy primarily. Okay? In the covalent bonding model, instead of having the transfer of electrons completely from one atom to another, we have primarily the sharing of electrons in pairs between atoms. And the import of this is that it's done in such a way that a stable electron configuration is obtained. And therefore, the atoms that you start with are at less stable positions energetically than the molecule you end with. The molecule more stable than the atoms. Now, each of these pairs of electrons shared between two atoms counts as 2 electrons for each one of the atoms when we're looking at the octet configuration that we discussed before, the S2P6 configuration. If 2 atoms share 2 electrons, the 2 electrons count for each atom in the counting process. And this is called a bonding electron pair, a pair of electrons shared between 2 nuclei, and sometimes we represent it with 2 dots like this, or sometimes we represent it with a line, but you know what it means, okay? It means a shared electron pair, or ultimately this is a single, what's called a single bond. So an electron pair in the valence shell that's not used in bonding, still a pair of electrons, but it's called a lone pair because it isn't shared. It belongs exclusively to one atom or another, and when you draw the Lewis dot diagram, it will be obvious how many lone pairs there are around each one of the atoms. And again, this is done in order to achieve an octet. So let's take the case of hydrogen fluoride. And now I'm going to ask you to just think about this in qualitative terms about the formation of hydrogen fluoride. So I'm going to take a hydrogen atom, which is not the way hydrogen comes, you know that, but conceptually I just want to look at the number of electrons here. I'm going to use the Lewis dot diagram to accomplish that. So I have a hydrogen atom, and I'm going to imagine that that combines with a fluorine atom, and I learned how to draw these Lewis dot diagrams for fluorine. And one of the things that I saw for group 7A elements is there would be 7 electrons, 3 pairs, and a single. And the way this is usually taught in some places, the idea is that somehow these 2 atoms come together and the fluorine's electron is shared with the hydrogen and vice versa, and you get a shared pair of electrons between the hydrogen and the fluorine. And the 3 lone pairs on the fluorines, so that gives 8 electrons around the fluorine, which is an octet, so that looks good. And then 2 electrons counted for the hydrogen. Sometimes that's called a duet, and that's all hydrogen can accept because it only has the 1 valence orbital, which is an s orbital, can only hold 2 electrons. So this picture shows that the octet is satisfied for this Lewis dot diagram. And it also shows over here, if you look at this part of it, what the lone pairs are, what the bonding pair is, and that the blue circles indicate the octet for the fluorine and the duet for the hydrogen. And down here at the bottom, a single line is used to replace the shared pair of electrons. All of those are acceptable ways to describe the Lewis dot diagram for hydrogen fluoride. Now, let me emphasize that that's not the way hydrogen fluoride forms. I just wrote it down that way so we could count that there are 8 valence electrons. Lewis dot diagrams are good for counting, and so that's why I did that. Okay, so this shows the formation of a single bond sharing a single pair of electrons between the 2 atoms and achieving an octet and an overall stable electron configuration for the molecule. So this is our focus now. We want to see what constitutes the most stable arrangement of electrons for the molecule that we're talking about. A little bit later, not too long, I'm going to give you a method for rigorously determining the Lewis dot diagram for a molecule. Okay, but I'm going to hold off on that for a moment until I lay the foundation for that particular work. So let's consider F2. For F2, of course, we have 2 fluorine atoms. We want to count the electrons. We have 1 fluorine, and then we have the other fluorine. And both of them have 7 electrons. So in order to get a stable electron configuration, 1 electron is shared from each fluorine, and a single bond is thereby made. Not saying it happens that way, I'm just saying you can describe the bonding that way. And as you see in the picture over here, the blue circles show the octet for both fluorines. And we can draw this over here like I did over there, if you wish. You've got to be sure to count the electrons. And you've got to be sure in the end that all of the atoms, like fluorine, have 8 electrons around them, that the octet is satisfied. That is necessary. And you need to do it in all the cases that we define as being sort of normal octet cases as opposed to expanded octet cases that we'll talk about later. So to summarize this, the covalent bond in H2, the one in HF, and the one in F2 is a single bond. It consists of a pair of electrons, and that's all we need to get an octet. Those are examples of molecules that contain only single covalent bonds. Other molecules can contain double and triple covalent bonds. If you go further up in inorganic chemistry, you'll find out that there are quadruple bonds too, but we won't consider any of those in this course. To illustrate, without showing you how it was derived, that's probably not the right word, created maybe, I'm going to use ethylene. Ethylene has 2 carbon atoms, so that's 2 times 4 is 8 electrons, and it has 4 hydrogens. That's 4, so there's 12 electrons to work with. And what we have to do is to figure out how to arrange those electrons so each carbon has an octet. We will never, in this course, consider stable molecules in which carbon has other than an octet. Okay, we won't. We just won't do it. If I do it later, you tell me, Dr. Geanangel, you said we never do that. Okay? Just assume that it's always going to be thus. So, how do you arrange 2, 4, 6, 8, 10, 12 electrons around 2 carbon atoms and 4 hydrogens to make sure everybody has an octet? Well, you have to share 2 pairs of electrons to do it. If you can think of another way, show it to me. Remember, you've got to get an octet. So the 2 pairs of electrons here correspond to a double bond, and so we draw 2 lines there. And single bonds between the carbons and the hydrogens. So we have 4 CH bonds and 1 carbon-carbon double bond. In a little bit, we'll talk about how double bonds are different from single bonds. Okay, I guess I've said that. Questions on double bonds? All right. Then a general rule to give you here. Multiple bonds occur probably 95% of the time between or among the atoms of carbon, oxygen, nitrogen, phosphorus, and sulfur. Okay? Sodium doesn't form any covalent bonds at all, let alone double bonds. But these are the elements that do. Another possibility, in order to achieve an octet, is that a pair of atoms will have to share 3 pairs of electrons. That would correspond to 6 electrons and what we call a triple bond. In the dinitrogen molecule, there is such a triple bond. Each nitrogen has 1 lone pair. 2 nitrogens is 10 electrons, and the only way to get an octet for each one of the nitrogens is to share 3 electron pairs. And of course, that corresponds to a triple bond. And there are also, in this Lewis dot diagram, lone pairs. So in N2, there are 2 lone pairs and 1 triple bond. Okay. We use the term bond order to represent the number of electron pairs that are shared between any 2 bonded atoms in a molecule. Okay, the bond order is a useful concept because it relates, it gives us information about bond energies and bond lengths and a few other things. To look at the examples that we've considered so far, a single bond, bond order 1, was seen in F2. It was also seen in HF and H2. A double bond was seen in ethylene, okay, C2H4. A triple bond was seen in N2. So those are the examples of single bonds and multiple bonds. Double bonds and triple bonds are considered multiple bonds. Now, what holds a covalent bond together? When I asked my high school teacher that, her eyes sort of glazed over, and she gave me an explanation that it was something to do with the stability of an octet. And that's true, but when you get right down to it, there's something under that if you focus on the bonds. So if we look at dihydrogen, we have 2 protons at a distance of the bond length, separation of the bond length of H2, whatever that might be. That's the distance between the nuclei. And in there, between those nuclei, is a pair of electrons. You can see them here. And the bond itself has a stability in that if you bring 2 hydrogen atoms together, there's a kind of welding torch that does this. If you bring 2 hydrogen atoms together and they form this bond, they release a lot of energy. It is called the bond energy, surprisingly enough. And in qualitative terms, at least, you can figure out why that's the case, because there are 2 repulsions from Coulomb's law here. Oh my goodness, he just used Coulomb's law to explain the stability of a covalent bond. How can you do that? Well, Coulomb's law still applies, right? These 2 positive charges repel one another. These 2 electrons have negative charges, both have negative charges, so they repel one another. That's what these red arrows are. But the positive charge attracts this negative electron, and this positive charge attracts it too, and the same thing down here. So these green arrows suggest there are 4 attractions, and the red arrows show that there are 2 repulsions. Now, in an arrangement like this, that means there will be net attractions. The bond energy, Be, is the amount of energy required to overcome this net attraction and separate the atoms back to wherever they came from. Okay? Pasadena and Deer Park. Okay? Wherever it was. So the bond energy is a stabilization that is due to Coulomb's law. A single bond, a double bond, a triple bond, it doesn't matter. Ultimately, there are more attractions than there are repulsions. Now, you can also illustrate that with a diagram like this. This is a topological diagram of the electron density in an H2 molecule. So this would be a hydrogen nucleus, and this would be a hydrogen nucleus. And you can see there is a maximum of electron density above this nucleus and one over here. And in the middle between the two, in this region here, there's shared electron density. And this diagram is telling us that that is representing the part of the electron pair that makes up this bond that spends most of its time in here. In other words, if you were able to take a snapshot, quantum mechanics wouldn't let you, but if you were able to take a snapshot, or maybe a time exposure, depending on exactly how you wanted to do this, these electrons would spend part of their time in here. And to the extent that they do that, then the attraction and repulsions that I show up here will be active, and that this will generate a bond energy, a net attraction. Here's how we represent that. If we had an AB bond, a diatomic molecule AB with a single bond, and we applied an amount of energy just equal to the net attractions over repulsions here, if we did that, that would be enough to create free atoms A and B. So this is putting in the bond energy of AB. If we take the AB molecule, we add that amount of bond energy, that's enough to break the bond. When you break the bond, it requires that the only way you can do it is to apply enough energy to be equivalent to or greater than the bond energy. So the process of bond breaking is always endothermic. If you want to break a bond, it will, in every single case, be endothermic. You'll have to put in energy. Any questions on that? And as before, if you reverse the process, as we learned in Chapter 6, and you form the bond, that will always be exothermic. And the energy change will be negative, minus the bond energy. It will be the delta H for this process. So breaking bonds requires you to put energy in. Forming bonds releases energy equal to the bond energy. Now, the magnitude of the bond energies are not possible for us to easily predict without doing some pretty complicated calculations. They clearly depend on the electron configurations of A and B. They depend on the nuclear charge of A and B. They depend on the radii of A and B. And Table 9.2 lists a bunch of them. We're not going to ask you to memorize any bond energies. Isn't that nice of us? Okay. But we just want you to be able to use them and interpret what they mean. Now, the bond length, as we said 4 or 5 slides back, is the distance between the nuclei of the two bonded atoms. The distance between the nuclei. All right. Now, bond lengths increase in a series of similar bonds as the atomic size increases, because as the atoms get bigger, they're naturally going to be further apart in the molecule. Okay? If you look, for example, at the dihalogen, four of the famous 7 diatomics are dihalogen. So these are 2-scale pictures of F2, where the bond distance is 143 picometers, Cl2, where it's about 200, Br2, where it's about 220, almost 230, and I2, where it's 266. All of these have the same bond order. What is it? It's just like fluorine was. You remember what the bond order of F2? It's bond order 1. 1 pair of electrons shared. You get that from the Lewis dot diagram. So they all have the same bond order. And therefore, the atomic size will dictate the bond length, not the bond energy. So we'll have to take a look at this in more detail, but if everything else is equal, the bond length will increase with increasing radius of one or both of the bonded atoms. Okay. Now, the effect of the bond order is easily predictable. A higher bond order, 2 instead of 1, for example, leads to a shorter bond length. A stronger bond is a shorter bond. A weaker bond is a longer bond. So a higher bond order results in a shorter bond length and, of course, a higher bond energy. So let's take carbon-carbon bonds. The 3 kinds of carbon-carbon bonds that we will be considering in this course would be carbon-carbon, single, double, and triple. The bond orders, likewise, 1, 2, and 3. Now I want to show you numbers. Don't let your eyes glaze over. You can deal with numbers. I want to show you first the bond lengths. The bond length, the typical bond length for a carbon-carbon single bond is 154 picometers. If you take organic chemistry, they will drum that into you until you'll never forget it until you'll be 100 years old. Okay? 154 picometers is a typical carbon-carbon single bond. If you go to a double bond, the bond order goes up from 1 to 2, and therefore, according to this, the bond length ought to go down. Well, it does. It goes down to 134. Isn't that interesting? And if you take a carbon-carbon triple bond, as exists in, let's say, acetylene, the bond order goes up to 3, bond length goes down again, down to 121. But I said a shorter bond was a stronger bond, and a longer bond was a weaker bond. So let's look at the bond energies. Don't let your eyes glaze over. Look at the number. 347 kilojoules per mole of a carbon-carbon single bond. 154 picometers for every one of them. If you go to a carbon-carbon double bond, look, it almost doubled. It didn't quite double. You can explain why it doesn't quite double, because if you put 4 electrons in a given space compared to 2 electrons in the same space, there'll be a few more repulsions. Electron-electron repulsions. But in any case, you can see it definitely went up in a healthy increase when the bond order went up. And as we said before, it's a shorter bond. And that means those 4 electrons are going to be squeezed into an area shorter and less volume than these 2 electrons were up there. So that's enough to make those repulsions greater. It's really very simple when you think about it. A triple bond, carbon-carbon, is 839 kilojoules. You don't have to remember these numbers, but you should be able to tell what the trend in bond energy is if you have the trend in bond order or the bond length available there. Questions on this table? I'm glad you didn't let your eyes glaze over, because now we have a problem. The problem is to arrange the bonds in each of these sets, A and B, in order of decreasing bond length and bond energy. It means we've got to find the biggest one and then arrange them in progressively smaller sizes. So we've got phosphorus fluorine, phosphorus bromine, phosphorus chlorine in the first set. And then we got carbon nitrogen double, carbon nitrogen single, and carbon nitrogen triple. So let's look at A first. All of these, you can see from the diagrams here, have a phosphorus halogen bond order of 1. So the differences in their bond length and bond energies won't depend on bond order, because they all have the same bond order. So what will it depend on? Will it depend on the phosphorus radius? No, they've all got phosphorus atoms, that's right. So it's going to depend on the size of the halogens. And we remember in the periodic table, fluorine's at the top, and then under it is chlorine, so that'll be bigger in the size trends we learned about. And then under that's bromine. So the bond length will increase in the order of the strength decreases. Here's what I mean. Phosphorus fluorine has the shortest bond because fluorine is smaller than the other halogens, and phosphorus is the same in all of them. And phosphorus bromine will have the largest. So if we're going to do it in terms of decreasing bond length, PBr will be the first one, because bromine's the biggest, and that's larger than PCl, and that's larger than PF. So that's the decreasing bond length. The strength works in just the opposite order. PF is the strongest, PBr is the weakest. Why? Because other things being equal, the nuclei and the electrons are closer together in PF than they are in PBr. Meaning, in PBr, the bonding electrons is spread out over a larger distance. And Coulomb's law says, whoa, larger distance, less energy of interaction. Okay. Questions on that one? All right. Looks like I didn't get my slides ordered here. Let's look at B. We have the bond orders. Carbon-nitrogen triple bond is greater than double bond, greater than single bond. The bond lengths will be in the opposite direction because low bond orders lead to long bond lengths, large bond lengths. So the largest bond length will be the carbon-nitrogen single bond, and the shortest bond length will be the carbon-nitrogen triple bond. The bond strength will be opposite, just like it was before. Carbon-nitrogen triple bond is the strongest, and carbon-nitrogen single bond is the weakest. One comment before we leave this subject. For different atoms A, in A like PF, PCl, PBr, the relationship only holds for single bonds. It doesn't hold for double bonds, and there are exceptions to it.